Today I'd like to show you a little Python script that I built to be able to inject signals into ngscopeclient. This is a very interesting piece of software with a number of professional features, and I wanted to learn a bit about how signals work at low level and use the method that ngscopeclient allows you to communicate with input devices through a TCP/IP network. In this case, we will use the input that ngscopeclient has for SDR devices, software-defined radio devices, and using that technique with a bit of Python, we'll be able to read the signals and encode them in a way that ngscopeclient can use, and begin to explore the options of this magnificent piece of software with things that everybody has, which is basically a computer and a microphone or audio input of any kind. So yeah, let's give it a try. First, we're going to install the script. We go to GitHub. You have the link in the description. Copy the URL of the repo and clone it. In my case, it's going to give me an error because I've done this earlier. Okay, we get into the folder that this clone operation has created and install the requirements. It should tell me that I don't need it because I've done it already. And if everything goes fine, we should be able to see the help options of the script. Here they are. And my suggestion is to start with this option with tone. This is going to generate a local signal, a test tone, and it's going to send that to ngscopeclient. And it's a good way to just get things going before we attempt to more complex operations. And the way I like to run this is keeping ngscopeclient running in the background, so I can use a single terminal. I think in this case it's going to be also useful for this video. So we bring it up, adjust a bit to the screen. Here we go. And with this ready, we bring the bridge with the option tone, nothing else. Okay, it's telling us that by default it's going to create a 2600 hertz signal, 48 kilo sampling, and the next step is to tell ngscopeclient to interface with this bridge. As mentioned earlier, we're going to use the SDR device type for this purpose. This could be a bit confusing because obviously we are not attaching an SDR device, we are pretending to be one. So we invoke add SDR option device, we select protocol twinlan, and we tell that we're going to use our local host. 2 ports for the twinlan protocol, 5025 and 5026, and we add. And here it is. Here we have you can see the new device has been created. And on the terminal, we can see also the way that ngscopeclient has to communicate with devices over the network. We can see the SCPI commands being executed, and the script is going to be translating some of those to operations that we need. So my suggestion is initially decrease the sample depth. The initial default is a bit too high. Let's say 2 kilosamplers per second, and we press play. We can see those lines going up and down that they don't make much sense at the moment, but if we go to it, we place our cursor here in the ruler and we zoom out. Now we can see that we are getting something. This is the script generating that tone. This tone is created in IQ mode and is sent in that format into the client. And if we stop here and we just a bit more here, yeah, we can see the characteristic waveform of a tone that has been decomposed or created in IQ mode. We can see one signal phase shifted respected to the other. And also we can see in the filter graph that the ngscopeclient offers is that it was, well, I didn't show you that, but at the beginning obviously this was empty, and now we have an input, which is the mentioned let's call it this pretend SDR client, which is at the moment is just helping us to inject a signal coming from our terminal. In this case it's a test signal, but we will get to more complex options later. So okay, yeah, just play again. And yeah, remember, if at the beginning you don't get this, you will probably have to do a bit of zooming in and zooming out before it gets to the scale that the screen requires. I'm not familiar with Windows PC running this client, but in the case of this MacBook, the way to zoom in and to zoom out in the ruler is using 2 fingers at the same time in the trackpad. Very easy, up and down, and yeah, here we have it. All right, so the next step is this signal is IQ, so we can tell the client to apply math. We can grab one signal, add it to the other, simple. And we come back to the waveform. Here the combined, the added signal is at the moment overlapped in this graph. We can see that ngscopeclient has created this add over here, and the first thing we need to do is to move it somewhere else so we can see it clearly. And my suggestion is to drag it to this little square that appears at the top of this graph to create a new graph for this signal, for the combined IQ signal. We need to do the same again. We need to zoom out the ruler. There we go. I think here's okay. Yeah, here's okay. And the generator will, as I mentioned earlier, will take the default settings, but using using the SDR interface, we can fool a bit in ngscopeclient and send some settings, change some settings through this UI to the tone generator. For instance, we can change the center frequency and say, okay, let's produce 4K Hz signal. Obviously, this center frequency in this UI refers to an SDR device, which in this case is not what we are doing, but this is a way we have to on the fly, without going to the command line again, without invoking everything again, we can change some settings. In this case, we're going to increase the frequency to 4000 Hertz. We play, and we see the change. Then we notice that for 400 Hertz, 4000 Hertz, the sampling frequency might not be what we need. We see the signal is a bit not perfectly shaped, so we can also increase the sample frequency to 96 kilosamples per second, and we press play again. Here we go. A much well-defined signal. All right. We can apply some measures to make sure that we are doing what we think we are doing. We can measure the added signal result, in this case frequency, and let's select trend. And another graph has been created, and you can see here that it's centered around 4 kilohertz. We need another options. We can adjust the ruler, zoom in, zoom out to see how stable is this frequency we are generating. It is stable. And we stop and we increase even higher to 5 kilohertz. Now the signal we had here has disappeared because we need to change the ruler again into final signal, and here it is. It's telling us that 5 kilohertz, the frequency we are generating in this test. While we are doing this, ngscopeclient is updating the filter graph, and those controls are not great for macOS. This is some work that the project is doing at the moment. Oh, too far. Here it is. Okay, so while we are adding measurements, signals, the filter graph will be in real time updating with these components, which I think is pretty cool and something that stands out in the ngscopeclient. Stop. So yeah, that's a good way to get things going, to make sure that our client is up and that our Python script is also working. I think it's for a test. It's enough for now. Next, we're going to use a Unix pipeline to send a file into ngscopeclient through the script. We have an example here on the page in Github. In this example, we are going to download a file that includes a signal of 50 kilohertz. encoded in via 250,000 samples per second, also encoded in IQ. In this case, this format used by a common SDR USB device uses 1 byte for A, 1 byte for Q. So every 2 bytes, every pair of bytes become a sample of the signal. It's not a great way to use this setup because ngscopeclient has its own ways to import files, but again, this is, I think, is going to help us to understand a bit more of what we are trying to do, which at the end of the objective is to feed into ngscopeclient real-time signal coming from any device in our computer. But this is a good way to familiarize ourselves with this concept. Okay, copy. Let's start ngscopeclient. And paste the command. I already have downloaded the file. It's in this folder. This is the name of the file, and yeah, we need to specify sample rate and encoding, because this is not an information that is transported through a Unix pipeline. The pipeline is going to grab every single byte that is included in this file and is going to send it to our Python bridge script. So we need to help the script and inform of some basic characteristics. One of them is the sample rate, and the other is the encoding format. Okay, let's see what happens. The cat command runs, sends the information to the script, and now when we add the SDR device, we can see that we don't need to configure localhost and the port again, because ngscopeclient remembers. We just need to select it. Here it is, and we press play. Same as before, we need to zoom out in order to find our signal. And here it is. Same as before, we go to filter graph to apply math. We add I and we add Q. Go back to waveform. The new signal has been created with the result. We drag it to this little square over here. We zoom out. And this is our resulting signal. And next, we can apply other functions to see what we have here. In this case, I think the best is just apply a simple spectrogram. We go to RF option, spectrogram. We don't need this, we can close it. The filter graph has updated with the new measurement. And we're having a similar issue. We need to zoom out to find our spectrogram. This is a side effect of the little trick that we are using to inject signals into ngscopeclient, pretending to be an SDR device. We are misleading the client, and because in here on the right scale, on the right ruler, is looking for a signal in much higher frequency. As I mentioned earlier, in this example, we are looking for a 50K signal. And zooming out, zooming in. And here we have it. Here we have the spectrogram. The center frequency aligns pretty well with 50K, which is the signal that we were originally looking for. Just a simple example, we can grab a file, send it to the pipeline, tell the script what we expect, and that will bring us this signal into ngscopeclient. Not the best way to do it. This is just an example to familiarize ourselves with this concept. ngscopeclient has better ways to import files, but today I think it's good to see this first example. Stop and stop. On the next example, we'll inject into ngscopeclient a signal coming from an external device. In this case, in this demonstration, it's going to be a microphone, but could be any other external signal that our laptop can handle. And we're going to use SOCs. This is an amazing tool. It's almost unbelievable the things you can do with this tool. You have it available for many operating systems. You have it, obviously, you have it in macOS. You have it in Windows, in Linux, and there is a lot of material out there. And it's out of the scope of this video today to explain, to go into detail on these features. The takeaway here is that we are going to use SOCs to do different things at the same time. We're going to use SOCs to get a signal, to modify it, to encode it, and to send it through the Unix pipeline to our bridge script. You have some examples here in the README, in the repo. The first example using SOCs is going to do a similar thing that we did earlier, reading from a file you can have it stored in your computer. But in this case, SOCs is going to create the IQ version. It's going to create the IQ components of this signal. This could be an audio file you can download, you can create. SOCs is very good using opening standard formats. In this case, it's a WAV file. And it's going to open this file, it's going to create the IQ components using a Hilbert transformation. It's going to resample the file, it's going to encode the file, and it's going to stream the results through a Unix pipeline. So we can do whatever we want once we have that in a pipeline and once we know the format we are expecting. In this case, in this example, we're sending this stream to our Python bridge, and that's going to send it to ngscopeclient. But I think what is more interesting for me, is to use real-time signals using the same principle, but the source is not IQ, but our SDR device, our Python bridge, and ngscopeclient expects the signal to be IQ. We're going to use SOCs to read from our microphone a specific sample rate, to use a Hilbert transformation to create the IQ components, encode it, combine into a 2-channel signal, and send it through the Unix pipeline into our bridge script. This is obviously, this demos is running in a MacBook. In your case, things are going to be different. If you're using a different operative system, I cannot really help you much in the case of Windows and Linux. There is a lot of documentation, but specifically for Mac users, let me show you something, because it took me a while. It took me a while to find the name of the devices that SOX needs in order to read in a MacBook OS. And I think this could be useful. This simple command is very helpful to list the audio devices that SOX can see is detecting in your MacBook. Again, different operating systems is going to be different, but this command saved me a lot of time to list which inputs and which outputs I have in my system. So yeah, so a little hint. Let's bring the system up. ngscopeclient app, and we are going to run the example that is going to read from the microphone and create the stream into a pipeline into our script. Don't be scared about those errors. What's happening is that SOX is reading the microphone, is sending all the information through the pipeline, and nobody is listening at the other end. So we are overrunning some buffers. Select and play. Zoom out. All right. Here we have the signal. Let's stop for a second. Let's reduce the depth. 100 kilosamples is a bit too big. Let's use 2 kilosamples. Play. Okay. Maybe we can handle a bit more. Stop. 5 kilosamples depth. Yeah. Same as before. We need to add the 2 components of the signal. In the way from the menu, the signal has been created. Drag, zoom out again. And here it is. Success reading from the microphone, doing the IQ transformation. Of course, this is an operation completely handled by this command line, so we know exactly what to expect. We tell our Python bridge the sample rate we should expect, the format, and ngscopeclient does the rest. Obviously, Python is a language that is not going to give you a lot of performance. As you can see here, we're running this pipeline at 48 kilosamples, which is perfectly fine for a number of audio applications, but it's CPU intensive. I think that higher samples per second will require higher and more powerful computers, and kind of this is not the objective of this project. We don't intend with this script to substitute any serious hardware device, any serious way to input signals in ngscopeclient. The aim of this project is to have a simple and low-cost way to familiarize ourselves with the project, with the system. The same way the same way we are running this script in this laptop, it might be running in another device of in the network, because it's using the twinlan protocol that ngscopeclient provides in order to read from signal sources on your network. So it has some of the key advantages of this software, but obviously for signals that don't require a lot of samples per second. So I hope you like it and you enjoy it. Thank you.